A knight's tour is a sequence of moves of a knight on a chessboard such that every square is visited exactly once. A knight is a piece in chess, and these are the types of moves it can make. 2 steps in one of the main directions and then 1 step to either side. Now, to get a feeling for the task, let's first try it manually. For instance, suppose we start here in a corner of the board. Where can we go from here? Well, we can go, for example, here. And from here, we already have a few more options to continue. For instance, as our next move, we can go here. Then here, 5, 6, 7, 8, 9, 10, 11, 12, 13. And now, let's take a moment to think about this situation. Where should we go next? Well, one strategy worth knowing is called Warnsdorf's rule. This means that we always go to a square with the fewest possible onward moves. So in this case, it would be here. Because from here, there's only one move we can make, namely this. And so by Warnsdorf's rule, we would go here. And the motivation for this strategy is that squares with the fewest onward moves are already hard to reach from other squares. And so it's good to visit them while it's still possible. And also in this way, we hope to detect as early as possible situations where a partial tour can't be completed. For example, what if we don't follow this heuristic? So let's say, for instance, that from 13 we continue here with 14. Then in this case, we've already made it extremely hard, maybe even impossible, to complete this tour. It's just a bit hard to see in this early stage, but it becomes clear if we continue, for example, with 15, 16 and 17 here, for example. And now it's obvious from here we can only continue with 18 here. And it's over, because there is nowhere to go from here. All squares we can reach are already visited. And when we try this puzzle, then we will frequently run into such situations that a tour can't be completed because there's nowhere to go. Now, let's describe such a tour with Prolog. What exactly do we want to describe? A sequence of moves, right? And to represent sequences, lists are often a good fit. So let's describe a list of such moves. And how do we represent a move? Well, one approach is to say a move is simply the next square that's visited. So like coordinates x/y. And we can easily write this as a Prolog term, using for example the infix operator /. However, to represent pairs in Prolog, it's more common to use the functor and operator dash. And we will do this. So with this approach, a knight's tour is a list of successive squares, represented as pairs of coordinates x and y. And note that we have asked here, how do we represent a move? And we'll come back to this later. So let's define a relation, say knight moves, which shall hold for a list of such moves. For instance, the empty list is such a list of knight moves. And a list with an element p, and possibly further elements p's, is a list of such moves if, and now we refer to an auxiliary predicate, knight moves underscore, which uses p as a legged argument to benefit from argument indexing on p's. And this auxiliary predicate shall hold for a list of knight moves p's that start from p. And we again distinguish 2 cases. If no moves remain, then it's a list of knight moves. And a list with an element p and possibly remaining elements p's must be in a certain relation to the previous element, say pref or p0, the start. Namely, and that's the key constraint, p must be reachable from p0 via a knight move. And further, p's must be a list of knight moves starting from p. And finally, what is an actual knight move? Well, it's a relation between 2 squares, x0, y0, and xy, 2 coordinate pairs. And the relation holds for these squares if the absolute difference between the x coordinates is 1 and that of the y coordinates is 2. So visually, a knight can move like this and vice versa, and like this and vice versa. So with these conditions, we already cover 4 possible moves. But there's more, because a knight can also move like this and vice versa, and like this and vice versa. So to complete this, we add another clause, exactly as one would expect. This is also a valid knight move, if the x coordinates differ by 2 and the y coordinates differ by 1. And one important point to understand here is this is just one formulation of what we mean with a knight move, out of many possible formulations. In fact, it's even only one formulation within this approach. That is, if you use this specific representation of moves as a list of coordinate pairs. And there is nothing that forces us to use this specific approach or this specific formulation. For instance, let's keep the general approach and formulate this differently. For example, we can write this as a disjunction of arithmetic constraints, using a dedicated CLBZ predicate for disjunction. And in that case, we must also use a dedicated constraint for conjunction. That's a declaratively equivalent way to express this, only instead of 2 clauses, we now use a single clause to state what holds. And it has the same meaning, but it's not equivalent in all respects. Notably, this posts more constraints and therefore puts more stress on CLBZ. And therefore the speed of this formulation depends more on the speed of the constraint engine of our Prolog system. And that may make it faster or also slower, because sometimes naive backtracking is faster than posting many constraints. And one thing we notice here is that this is quite similar to a partially evaluated fold from the left, fold L. This is part of the Prolog, and in Scryer Prolog it's available in the lists library. And we see that fold L is like a more general version of knight moves underscore, because fold L takes a partial goal as the first argument, and if you plug in knight move as that goal, then many of the other arguments have the same shape. There's a list and a relation between states, relating the current state A0 and P0 respectively to the next state, A1 and P. So these argument pairs form state differences. And in a recursive goal, we refer to the tail of the list and the next state. So all these arguments have the same shape. And fold L has an additional argument, the final state A. And if we simply ignore that final argument, then the only remaining difference is this L here, referring to the first element in the list. Now imagine that knight move takes such an argument. Then it's completely clear that knight moves underscore can be expressed in terms of fold L, where we specify knight move as the partial goal and the last argument is simply ignored. Okay? This means that we can get rid of this entire definition of knight moves underscore if we make a small adjustment to knight move. Namely, we must introduce a new first argument which is identical to the third argument. Because now we have the shape required for fold L. The first argument is an element of the list, and the second and third argument form a state difference, a relation between the current state and the next state. So now we can use fold L like this. Procedurally speaking, we can think of this as going through all squares P's and describing a knight move from the previous square x0, y0 to the current square xy. And then making xy the new previous square. And we ignore the final square, because it doesn't matter. And this is obviously shorter. On the other hand, we also had to pay a price, because we had to, in a sense, artificially introduce an additional argument for a knight move, this xy as the first argument. Was it worth it? Well, in my opinion, yes. Because this version is easier to read, because it's shorter, and also we immediately see that it's a fold from the left, and we know this pattern. Now, regarding the formulation itself, we remember that we previously had 2 clauses here, and now we have a disjunction expressed with CLBZ. So, as already mentioned, this puts more stress on CLBZ, and depending on the speed of CLBZ, this may be faster or also slower, so it can also be a drawback. One potential advantage we get from this is that CLBZ now sees all the posted constraints at the same time, instead of seeing some of them only on backtracking. And therefore, at least theoretically, the constraint engine can perform clever reasoning on the entirety of all constraints. For instance, taken to an extreme, it could even recognize that we are describing a knight's tour and use a dedicated algorithm tailored to this specific problem. That's of course quite unrealistic, but at least theoretically possible now. On the other hand, there are now quite many constraints. We have arithmetic equalities, conjunctions of constraints, and still a disjunction. Not as separate clauses, but as a CLBZ constraint. And the bad news is that such reified constraints tend to propagate very weakly. So even though theoretically the constraint solver could apply very clever reasoning, in practice that's simply too much to expect, because it would be too costly in practice to reliably recognize all special situations. And therefore, the way we express a problem in terms of constraints can have significant impact on performance. For instance, in this specific case of knight move, we could state the constraints in a quite different way. We could say this holds if x is x0 plus a distance dx, y is y0 plus a distance dy. These distances, dx and dy, are one of -2, -1, 1 or 2, and finally the absolute distances must sum to 3, because that's how a knight moves. 2 steps ahead and then 1 step aside. So that's a quite different way to express this. Even though declaratively the formulations are equivalent. They describe exactly the same set of solutions again, as we can also easily test for a chessboard. This also means that we could even keep both definitions in the same program. That would be pointless, of course, and lead to redundant solutions. So let's keep only the new definition. Why this one? Well, for one thing, it has significantly fewer constraints, right? There are now only 3 instead of 4 equality constraints. And no more conjunctive CLBZ constraints. We're now using plain Prolog conjunctions. Further, there are no more disjunctions. Or rather, looking at this domain, disjunctions are now confined to choices between domain elements. And that's a good thing, because the constraint solver can very easily reason about remaining domain elements and use the sizes of domains for heuristics. And therefore, it's much better to have a disjunction in this sense, a choice between domain elements, than a choice between entire constraints. And on top of it, this definition is also quite easy and natural, certainly not much harder to read and write than before. Now, to actually run the program with Scryer Prolog, we also need to load a few libraries. First, because we're using integer constraints, we load the CLBZ library. Further, we're using fold L, which resides in the lists library. And let's also load library pairs, because it's useful when reasoning about pairs, which we're using here. And finally, we also load library lambda. This will come in handy in a moment. These are all quite portable libraries, and other Prolog systems such as Trailer Prolog also ship with them. And one useful setting we can add is CLBZ monotonic. This enables the monotonic execution mode of CLBZ, and that's very useful for declarative debugging and reasoning, okay? So this is our definition of a sequence of knight moves. Well, let's ask a few queries. A good starting point is always the most general query, where all arguments are variables. So we are asking, are there any solutions at all? In this case, any knight moves MS. And in response, Prolog tells us, yes, the empty list is such a list of knight moves. It fits the definition. A list with one element is also such a list of knight moves. And on backtracking, we get more and more answers for lists with longer and longer lengths. And most of these answers describe many concrete solutions. And if we look, for example, at these two answers, then we see that these are lists of pairs as intended, because that's how we represent squares, as pairs of coordinates. But there's also a case of an overly general answer, because this answer says every list with exactly one element is a list of knight moves, even if the element doesn't denote a square. And this may sound bad at first because it's unsound, but on the other hand, such overgeneralizations also occur elsewhere. For instance, if we consider the lists library again, and specifically the predicate append, then we see the Prolog definition of this predicate, where the second and third arguments are not constrained to lists. And therefore, for instance, with this query, we get a ground solution that is not even a list. So the predicate is overly general in the sense that it holds for more than just lists. And in the case of append, this is accepted practice. It holds for all intended cases as a relation between lists, and also for cases beyond that. And analogously, we can also say here, it holds for all intended cases where the element is a square, so it's complete, and also for cases beyond that, which we don't really care about. Then what about termination? If we add false to the query, then it cannot succeed, and only termination remains to be observed. And in this case, the query does not terminate. And that's expected, because the predicate is supposed to describe infinitely many answers. So we interrupt this with Control-C, okay? Now, what about lists with known length, such as, say, a list MS with exactly 3 elements? For this, the query terminates. And that's of course exactly what we hoped for. For a list of known length, the relation should terminate. Okay, so we've seen several answers. What about concrete solutions? That is, ground terms that satisfy these constraints. And here, library pairs comes in handy. With pairs keys values, we can relate the list of pairs MS to their components, X's and Y's. And we can use append to relate X's and Y's to their concatenation, the list V's. And due to our representation of knight moves, this list V's is a list of integer variables. So we can use label from CLBZ to generate concrete solutions. But this yields an instantiation error because the list V's is not sufficiently instantiated. That's because labeling only works on integer variables with finite domains. So what we do is we constrain V's to integers between 1 and 8. That's all we need for a chessboard. And now we get a concrete solution. That is an answer substitution which makes all variables ground. And on backtracking we get more solutions. Now let's think about it. Actually we only care about MS, the sequence of knight moves, right? The other variables don't matter to us. Yes, we need them in the query, for instance for labeling, but in solutions we don't really care about X's, Y's and V's. Also because there are completely obvious relations between all these variables. So MS is all we really want to see in answers. Now, how do we do this? Well, one way would of course be to print such answers ourselves using side effects, and maybe also a failure-driven loop to emit all answers. There's also a much better way, namely to use library lambda. Because one interesting use case of this library is that it lets us project away uninteresting bindings. For instance, in this example, we are only interested in bindings for MS, right? So what we do is we say that MS is a free variable within the scope of a lambda expression that has no parameters and consists of the entire query. And we can indent this a bit better. And now the system reports only bindings for MS. So this is a very useful application of library lambda. It lets us focus on the bindings that matter to us. Now, regarding these solutions, let's take for instance the first one. What does it describe? A sequence of knight moves starting at square 1, 1, then going to 2, 3, and then again to 1, 1. So yes, these are knight moves, but it's of course not a knight's tour, because a knight's tour must not visit a square repeatedly, or in other words, the visited squares must be different. So what we need here is another constraint, say different squares. And this relation shall hold for the empty list, because all squares in it are different, and also for a list with at least one element p, a coordinate pair, and possibly remaining pairs p's, if p is different from all elements in p's and p's are different squares. Now, when are two coordinate pairs different? Well, if their x components are different or their y components are different, right? And that's it. We now have everything we need to describe a knight's tour. How should we call our relation? Well, it's obvious, right? Knight's tour, of course. But unfortunately, that's not a valid predicate name because of the apostrophe. So we would have to put it in single quotes, and even more, to represent a single quote within single quotes, we have to add an additional single quote or a backslash. And the resulting name isn't very readable, right? We could of course remove all single quotes, but that would change the meaning of the name. We are describing a knight's tour, not a knight's tour, right? So maybe let's just stick with tour and say we're describing a tour T's, and by such a tour we mean a list with 64 elements, namely 64 knight moves in our representation, so 64 squares. And these squares are all different. So this predicate is what we call a core relation. It states the constraints. And by convention, the last argument of a core relation is a list of all variables that need to be labeled. So we add an argument here for the variables v's. But now, of course, the name tour no longer fits the arguments, because the predicate no longer describes only a tour, but now has an additional argument. And for such cases, a useful naming convention is to append an underscore to the name to indicate that there are additional arguments. So we change the name to tour underscore. Now, what exactly are v's, the variables we want to label? Well, it's clear, right? These are simply the x and y components of the squares in t's. And we can use, for example, pairs keys values to relate t's to x's and y's, and append to say v's is the concatenation of x's and y's. That's one way to do it, and very straightforward. Though one drawback is that v's now starts with all x coordinates and only then all y coordinates follow. And as a consequence, when we now label v's from left to right, for example, then we get a rather counterintuitive search process, because the search now doesn't yield a succession of squares, but tries to find solutions for first the x coordinates and then the y coordinates. So the intuitive connection between these coordinate pairs is lost. And that may be good or bad. We'd have to try it to find it out. However, in any case, we often prefer to have more control over the order of variables. And we can easily get this here with a relation, say, squares variables relating t's to v's. And often a DCG non-terminal is even more convenient, such as here, where we say the variables in the list v's are, for each square in t's, the x coordinate and then the y coordinate. And of course we can also define this in other ways, and I leave trying different variants as a challenge. What else can we do here? Well, we can, for example, generalize the definition, because here a concrete number occurs, the length of the tour, and we can generalize this to n, and we can add this n as an additional argument of the relation, and also adapt the name to n tour underscore. So now it's more general, and we can now also easily test the approach with smaller instances. So this is our definition. Now let's ask a few questions, such as, for a chessboard that is 64 squares, does the core relation terminate? Yes, it terminates. And that's of course great, because an important guarantee of CLBZ is that labeling always terminates. And therefore, if the core relation terminates, then the core relation plus labeling also terminates. So we know that even if the search takes a very long time, the system is not stuck in an infinite loop. And for concrete solutions, we label the variables, using for example the predicate labeling. The first argument are the labeling options, we use the empty list for the default options. And now we get an instantiation error. That's because to guarantee termination, labeling requires that all variables have finite domains. So as an additional constraint, we say that v's are integers between 1 and 8. And now, when we post this, first it takes a while to set up the constraints. And once they are all posted, labeling searches for concrete solutions. And we see that the search is very fast. Prolog quickly tries many different values for variables. And it also seems to progress nicely. In fact, it at least seems that we've already constructed almost a complete tour, right? More than 50 squares are already occupied with only a few remaining. So it seems that we've now almost found a solution. Well, it may seem that way, at least at first sight, but it's not the case. In fact, there's a major problem here, and if we look a bit more closely, then it's clear that many of the partial tours that arise here during labeling can impossibly be completed to a full tour. Why? Well, we only have to look at this square. We see that in many cases, this square can no longer be reached from any other square, because all squares that can reach it are already occupied. And even if we do reach it sometimes, then there's nowhere to go from here. At the same time, we see that Prolog does a lot of work. It searches very hard for solutions, and it's good at this search, it's very fast. But in a sense, this is all wasted effort, because it doesn't address the root of the problem. What we see here is called thrashing, repeated backtracking due to the same reason. So, no matter what Prolog does from here on, and no matter how fast it is, it cannot complete partial tours that have such a fundamental issue, an unreachable square. The only way to solve the problem is to go back to where the problem arose and to fix the root of the problem. And if we search naively, then it takes a very long time until Prolog backtracks to where the problem arose, because there are so many possibilities that still need to be tried. So what we want now is not necessarily a faster search, because the search itself is quite fast, but a way to avoid or at least reduce thrashing. And the good news is that Prolog can help a lot to reduce thrashing. There are several techniques we can try. One of the easiest is to try different labeling strategy. For instance, FF, first fail. That's often a good heuristic. So let's try it. Now, what is this? Well, apparently the variables are now tried in such an order that only one square is placed definitively. That is, so far, we know the x and the y coordinate only for one square. That's this single square labeled 1 here. For the other moves, at most one of the coordinates is known, and so they are not shown here because we don't yet know where to place them. And this makes it hard to tell how successful this strategy is and how close we are, roughly at least, to a solution. It appears though that this strategy is not particularly effective either. Another thing we can try is breaking symmetries. But at least for this problem, it seems hard to break symmetries without losing solutions. For instance, if we demand that the squared position 1, 1 is the first square, then we are most likely already losing solutions. Because this may be an intermediate square in a tour, and a tour is directional, so we can't simply say that we always start here. Another thing we can try is to use different constraints. For instance, if we look again at our formulation, then one constraint that stands out negatively in a way is this disjunction of reified constraints. This is bad because, as already mentioned, such disjunctions tend to propagate very weakly. For instance, let's take these concrete coordinate pairs P's and an additional pair with unknown coordinates x and y. And we demand that all these squares are different by using the above definition. And to illustrate the issue in a simple case, let's say that x and y are between 1 and 4. So we are reasoning about a 4 times 4 board where 4 squares are already occupied, 1, 1, 2, 1, 3, 1, and 4, 1. And the question we ask with the query is, what are possible values for x and y between 1 and 4 so that the square xy is different from these occupied squares? And when we post the query, we get an answer from Prolog. In this case, Prolog tells us that, among other constraints, y must be between 1 and 4. 1 and 4. And this is an example of what I mean with weak propagation. Because we know that y can impossibly be 1 in this situation, because there is no remaining free square in rank 1 of this board. We also say the domain element 1 has no support, because there is no compatible x for it. Yet the constraint solver in this case has not eliminated 1 from the domain of y. It's still here and must be considered during search. And it also influences heuristics that take into account the size of the domain. So the solver doesn't even ensure bounds consistency in this case, because not even the boundary values of all domains are consistent with each posted constraint. There's a boundary value 1 that is not consistent with the constraint that the squares are different. A bounds consistent constraint solver would compute a different domain for y, namely between 2 and 4. And as mentioned, this weakness is also due to the way we have expressed the problem. The reified disjunction we've used makes stronger propagation computationally prohibitive. Or at least the constraint solver has favored propagation speed over strength in this case. Now let's think about it. How else can we express this relation, different squares? Well, one way to get rid of the disjunction is to say we associate each square with a unique integer. And so each move corresponds to an integer denoting a square. And for such variables, we don't need a disjunction. We can simply say directly that they are pairwise distinct. Now, how do we map squares from pairs of coordinates to integers? Here's one way. Let's simply regard a square xy as an integer in base 8. So we can use an arithmetic constraint to say for each square xy, the integer I is x times 8 plus y. Okay? This means that the squares correspond to integers like this. We can tweak this a bit so that the integers start from 0. So in this way, we associate each square with an integer, and that lets us eliminate the disjunction. How strong is the propagation now? For example, suppose we are reasoning about a square with coordinates x and y between 1 and 8, and that square is associated with the integer I. And further, suppose that all squares in rank 1 are occupied. This means that I must be different from 0, 8, 16, 24 and so on. And we note that this creates holes in the domain of I. It's no longer an interval. Then when we post this, we see that the domain of y still contains the integer 1. So again, that's weak propagation. And this happens even though the constraint solver knows, in a sense, that 1 cannot be part of a solution. Because if we explicitly ask, is there a solution where y is 1? Then Prolog correctly says, no, there is no such solution. Also, the previous formulation correctly yields this. And that's nice, but it's too late. We don't want to find this out only when we actually try the assignment, but earlier. We want stronger constraint propagation, at least bounds consistency, and ideally more. For instance, in this case and with these domains, the arithmetic equality has no solution where y is 1, and the constraint solver even knows this in a sense. 1 is a domain boundary of y, and therefore, at the very least, we expect the constraint solver to remove 1 from the domain of y. But with the current formulation, this doesn't happen. We again don't even get consistent domain boundaries. Because already this very simple situation, where we have a simple arithmetic relation and one of the variables has holes in its domain, this is already too involved to detect that 1 can be removed from the domain of y, or rather, the cost of this propagation was deemed to outweigh the advantages we get in such cases. For efficiency, arithmetic constraints tend to ensure only a quite weak form of bounds consistency that doesn't take holes in domains into account. So this formulation also propagates very weakly. But this general idea of associating squares to integers is still valuable, because it lets us eliminate the disjunctions. We only want to make better use of the domain information. We've seen that arithmetic constraints propagate too weakly if disequalities are posted and therefore holes in domains appear. But there are other constraints that take such holes fully into account. For instance, in our case, we can also express this equality of squares by using the constraints tuples in and all different. We start by describing a table, say squares table. And we want to state that T's is a list of triples, that is lists with 3 elements, where each element contains the x and y coordinate of a square and, as the third element, the unique identifier, the integer ID of that square. And we compute the ID exactly as before, in such a way that each square gets a unique ID. And T's is simply the list of all solutions. So our table T's is this, a list of triples, exactly one for each square. And the ID of each square, 0, 1, 2, 3 and so on, is the third element in each triple. And in addition, we define a relation pair triple ID to relate a coordinate pair to such a triple, where the third element is the ID of the square. And with these building blocks, it's easy to express that squares are pairwise different. First, we relate the pairs to such triples and IDs. So we extend each pair to a triple with a free variable as the last element to denote the ID. Second, we demand that T's is the squares table described above. And now we use the mentioned tuples in constraint to say each of the triples is an element of the table T's. So this is how we associate each square with a unique ID. And as more becomes known about the coordinates, also more becomes known about the ID and vice versa. Exactly as before, where we used an arithmetic relation, but now expressed in a different way using tuples in. And also as before, we can use all different to say all the IDs must be different. That's a key attraction of these approaches. Instead of a disjunction, we can now use this single constraint to express that the squares are different. So this is another attempt to express different squares. And for comparison, let's try again the situation we had before. A 4x4 chessboard where all squares in rank 1 are already occupied, and the square with coordinates x, y can therefore not be placed in rank 1. And from the answer we see this formulation has a clear advantage over the others we've tried. Prolog now detects that y must be at least 2. So that's a stronger form of consistency than before. This is bounds consistency, because the computed domain boundary is consistent with each posted constraint. In this case, it's even consistent with all posted constraints taken together, so it's even part of a solution. And in fact, even more holds. We've now tried this with rank 1 completely occupied. Let's try it instead with rank 2. And from the answer, we see that this formulation propagates really strongly. It removes inconsistent values not only from the domain boundaries, but even from the inside of domains. In this case, 2 is no longer an element of the domain. This stronger form of consistency is called domain consistency, because every value in the domain is consistent with each posted constraint. This is due to tuples in, which takes the domain information fully into account, and also reasons about holes in domains, instead of only the domain boundaries. So we've succeeded nicely. First, we have now eliminated the disjunction as intended, and second, we now benefit from much stronger propagation. And in addition, tuples in and all different are so-called global constraints, because they express a relation about many variables at the same time. And therefore, they have the opportunity to see more at once than many smaller and more local individual constraints would. And therefore, they can propagate more strongly. Whether they use this opportunity for strong propagation depends on the implementation. It's always a trade-off between strength and speed of propagation. In this case, we get quite strong consistency already from the tuples in constraint. This helps to reduce the search space, and that's of course good. On the other hand, constructing a table quickly becomes infeasible when there are more variables or the domains become larger, because all possibilities must be explicitly enumerated as an extensional relation where all tuples are explicitly manifested. And this doesn't scale well, and that's a price we pay for this constraint. Now, let's try to find a tour with this formulation. And what do we see? Well, the search is even faster now, probably because there are now fewer constraints. But again, a lot of thrashing. So that's a bit frustrating, right? We've now tried several different formulations, 2 or 3 different ways to express a move, and 3 different ways to express that the squares are all different. And we only get thrashing again. Why? Well, it appears that the system has painted itself into a corner here, mostly because it, in a sense, doesn't understand one important aspect, namely that the tour must be connected. And therefore, there's again a major problem here, the same as before. In fact, it's even at the same square as before. Even if we manage to reach this square, then there's nowhere to go to, because this square has become too isolated. We know this, we can see it. But all the formulations we've tried so far apparently don't adequately convey this to the solver. And therefore the constraint solver doesn't see the root of the problem, the underlying cause. Because the constraints we are using make it too hard to see, they are too local. Locally, that is just from where we currently are in the partial tour, it may seem that we can still complete the tour, because we can still make further knight moves to different squares, and there are enough free squares left. But if we look at the entire chessboard as a whole, then we already see that we can't complete many of these partial tours. So what would help here is a global constraint that detects as early as possible that a square has become too isolated, like this, and then prunes the search immediately. And for this, it's not enough to think about different formulations of just knight move and different squares. That's not the bottleneck here. For instance, from the perspective of just different squares, the situation still looks okay. There are still different squares left. But from our perspective, from the perspective of trying to find a knight's tour, the situation now looks highly problematic already. So what we need is a way to convey the overall goal more directly to the solver. We want a tour that visits each square exactly once. So let's go further back, way back to the start. At the start of all this, we said that this is one approach. And instead of approach, we can also say this is one model. It's one way to model the task. What does this mean? Model stems from the Latin word modus modi, and it means measure, rule, manner. It's related to meditare, to ponder, study, rehearse. And model has several meanings. For instance, in logic, a model is an interpretation that makes a formula true. Or as another example, a statistical model is a set of assumptions, a theory about sample data. And in constraint programming, modeling a problem means to express it in terms of constraints. So a model in constraint programming is the way in which we express a problem. And there's a linguistic aspect to this. We can think of the available constraints as a vocabulary of abstract concepts. And we must find ways to express our concrete problems in terms of these concepts. And the model can have significant operational influence. It may, for example, affect how fast we find solutions. And it may also affect how easily we can express our task. One sentiment I sometimes see about declarative programming is what, not how. And at least in my opinion, this does not adequately characterize declarative programming. In fact, as a consequence of what we just said, we may rightly say the opposite. How, not what. Because it matters how we express our task, not what is being executed. And personally, I never understood what the slogan in this form is supposed to mean, because what is what? In fact, when I took a course on functional programming, the instructor, a very respected expert, said, the how counts, not the what. And then said, no, excuse me, the what counts, not the how. So I'm not the only one who finds this very easy to confuse. What we can say is declarative programming means stating what holds as opposed to what is executed. The models we use are often declaratively equivalent. They express the same set of solutions, but procedurally they are often different. For instance, because different constraints have different pruning power. More pruning power may make propagation slower because it costs more computation time. And it may make the overall process faster because strong pruning reduces the amount of search. So, as mentioned, propagation is a trade-off between strength and speed. And depending on the task, strong propagation can be worthwhile. And modeling likewise and also therefore involves various trade-offs, such as how natural is the model. For instance, how do we denote a square? We use coordinates like 2, 3. And there are also other options which are also used in practice, or were used in practice in the history of chess. And for example, to a chess expert, some of these notations may seem a lot more natural than others. Also, is the model easy to understand and adapt? Can we use the model for variations of the problem? Can the model break symmetries, for instance by imposing ordering constraints? Does it allow good pruning, for example by using powerful global constraints? And is the propagation efficient or is it too costly? Is the formulation portable to other Prolog systems? Or does it use highly specialized constraints? And so on. One advantage we commonly get from declarative approaches is their generality. Declarative programs describe the situation, and we can use the same description in different modes to find, complete, and test solutions. This is in contrast to imperative approaches, where we usually don't get this benefit. Now, let's think about it. How else can we model a knight's tour? And initially, it may feel tough. We may think that we are left alone with this question. But we are not. There are many examples for modeling problems with constraints. We can study them and use them for guidance. And also, it's really interesting to think about it. How can we best use the available constraints to express tasks in different ways? Sometimes we don't even need constraints. Simple problems can often be solved with heuristics, such as Warnsdorf's rule, which we've seen. But for more complex problems, we'd appreciate all the help we can get. And that help is available in terms of supported constraints. For instance, we can visit the documentation of library CLBZ and take a look at the combinatorial constraints. These are powerful global constraints, and it's good to know a few of them. For instance, we've already tried tuples in. In our case, it didn't help a lot, but it's useful to know. As another example, global cardinality is a very powerful constraint, also good to know. It's a generalization of all distinct, also with very strong propagation, domain consistency. And as another example, there's a constraint called circuit. It holds for a list of variables that describe a Hamiltonian circuit. And as already mentioned, with such declarative descriptions, we can solve problems that heuristics and imperative formulations can't directly solve. For instance, the case where a solution is already partially known, and must be completed to a full solution. Now, let's try to use the global constraint circuit to describe a knight's tour. Here's the description again. The constraint holds for at least v's of integers if and only if they induce a Hamiltonian circuit. That's a cycle in a graph that visits each vertex exactly once. And the representation may seem a bit unusual at first. The kth element of v's denotes the successor of node k, and indexing starts with 1. So let's consider an example. Say we have a graph with 4 nodes, A, B, C, D, and we are looking for a Hamiltonian circuit, a cycle that visits each node exactly once. This is a solution. We read it as A is 2, so the successor of A is the second element in the list. That's the node B. From B we go to C, then to D, and then back to A, because D is 1. So that's the first solution. And on backtracking we get all solutions. And we note that we're describing only a subset of Hamiltonian paths, namely Hamiltonian circuits. So we end at the same node where we started. And therefore, if we use the circuit constraint naively, then we describe a subset of knight's tours. Whether it's a proper subset, we don't yet know. It seems likely, but at least theoretically, every knight's tour could be a closed tour. A closed knight's tour means that at the end of the tour, we can make a knight move to the start. So we could immediately repeat the same tour. So to be certain that this is a proper subset, we have to show that there's a tour that's not closed. But the main question we have now is, how do we use the circuit constraint at all to model the problem? Well, what we do is we regard each square as a node in a graph. And there's an edge between two nodes if and only if they are connected by a knight move, okay? And then a knight's tour is a Hamiltonian circuit in this graph, like this. So in this way, we describe closed knight's tours in terms of the circuit constraint. And this is now a quite different perspective on the problem. We're still describing a knight's tour, and we're also still describing moves, yet the representation of the tour is now very different from before. And let's start by relating a coordinate pair xy to a unique integer k. So we say xyk holds for xy and k if, and now we state our equation again and slightly generalized. We say we regard k as the integer xy in base n. So instead of 8, we now use n to make it more general. And we also make n one of the arguments, okay? And consequently we call the relation n xyk. So it's more general and in fact also too general. This does compute k if n, x and y are known, but if only n and k are known, then this isn't yet specific enough to compute x and y. For this we need to add a constraint, namely that x and y are between 1 and n. And now it yields concrete solutions in both cases. And for circuit, node indexing starts at 1, not 0. And so we don't subtract 1 now, okay? Now let's use this as a building block to describe which squares are reachable from a square from. So we say there's a knight move between from and to if x and y are the coordinates of square from, and the coordinates depend on n, the size of the board, so the relation also depends on n. And now let's think about it. What must hold about the coordinates of the squares? Well, we've already described it before as certain arithmetic relations. So we can simply reuse this here and say the coordinates of two, xt and yt, are x and y plus deltas or distances, as we called them before, dx and dy. So we again constrain these differences to form a knight move. And as mentioned, 2 is the square with coordinates xt, yt. And we use label to yield concrete solutions, and that's it. And note how we benefit from the generality of n, x, y, k. We use the same predicate to, procedurally speaking, compute the coordinates from a given integer and also the converse, to compute the integer from the coordinates. And to capture this generality, we say that the predicate describes or defines the relation between the coordinates of a square and the corresponding integer. This wording captures both usage modes and also more. Now let's ask, on a standard chessboard 8x8, are there any squares 2 which are reachable by a knight move from square 12? Yes, square 2 is reachable. Also 6, 18, 22 and so on, okay? Now let's again define a tour, this time as a Hamiltonian circuit. So we again define the relation n tour underscore of n t's and v's. And if we use the successor representation of circuit, then v's itself describes the tour. And therefore we don't even need t's anymore. And now we don't need an underscore anymore, because there are only two arguments, n and the tour. So the name fits, n tour. Now, what must hold for v's so that it describes a tour? Well, first of all, it must have the right length, namely n squared. And n is a natural number. And second, v's must describe a Hamiltonian circuit. So here is where we use the circuit constraint. And third, it must be a circuit on the intended graph. So let's call this a knight graph, and this must hold for v's. Now, what exactly do we mean with a knight graph? Let's define it. A knight graph consists of nodes. We say if there are no nodes, then it's a knight graph. And if there's at least one node v, and possibly further nodes v's, then what must hold for v? Well, the domain of v must be exactly the possible successor nodes. So the domain of v must be all squares represented as integers that are reachable from v. So let's use findAll to collect all integers 2 that are reachable from v via a knight move. Our relation knight move takes 3 arguments. N, the size of the board. We don't have n available here, so let's make it available as an argument. And also here, where we don't need it. And we pass along this n so that we have it here, okay? The next argument is the square from which we move. And the square is denoted by an integer. So for the second argument, we must specify the index of the node v in the list. Because we are interested in the possible successors of the node with this index. And again, we don't have the index available here, so let's again add it as an argument. And let's stop for a moment here and try to recognize the pattern again. Because this is again starting to look similar to a fold. We have as main arguments a list and as the current state an index. And for a fold, we need to describe a state difference by relating the current state, in our case the index, say index 0, to the next state, which is in our case the next index, say index. And if you use fold, then it suffices to define this relation for a single node v, and we can remove this fact. And now we have the shape for a fold. We fold over a partial goal, knight graph of n, the list v's, starting with index 1 as the initial state, and we ignore the final state, okay? Now let's complete this relation. We're looking for all squares 2 that we can reach, and we use findAll to collect these squares, these integers, as a list t's. And now we're almost done. We now only need to relate these integers t's to a term dom, the domain of v. Because then we've set up the desired graph. The domain of each variable v contains exactly the admissible successors, the nodes that are reachable from v. So how do we describe the domain? Well, it certainly involves t's. And let's see if we can use fold L straight away. So we fold over the integers t's and we need an initial state. What is the initial domain? Well, suppose that we know an integer t that's definitely in the domain. Then we can use t here. And the final state is dom, the domain we want to describe. And for t, let's simply take the first integer in this list. And there's bound to be one, because every square has at least one square it can reach. And now we only need to describe the relation between an element of t's the current state, and the next state. And for brevity, let's do it as a lambda expression. So the arguments are an integer I from t's, the current domain d0, and the next domain d. And how are they related? Well, the next domain d is the current domain d0 or I. Written like this, it may seem a bit unusual at first. So let's consider this goal in isolation. And let's ask Prolog, what do solutions look like in general? And in response, Prolog tells us this is the shape of terms we are describing. So these are answers, and each leaf answer describes infinitely many concrete solutions. This may still look a bit strange, so let's try it with ground terms like this. Now we get a single concrete solution, and this is the shape of the term. And we can read it as 0 or A or B or C. That's of course not a valid domain, because A, B, C aren't integers. But it illustrates the shape of the term we're describing here, okay? And if we use the integers t's and t here, then it's a valid domain. So dom, and thus the domain of V, contains exactly the indices of the successor nodes of V. And that's precisely what we need for circuit. So this describes what must hold for V. And now we only need to relate the current index, index 0, to the next one. And that's of course easy. The next index is index 0 plus 1. And we're done. Well, there's one thing we can still improve. Consider how we're setting up the constraints here. We post circuit very early, as one of the first goals. And every time we constrain one of the variables, this circuit constraint takes the domain changes into account. For instance, posting this in constraint causes propagation of circuit. And this gives rise to a purely operational or procedural consideration. We know that each variable in V's is involved in the circuit constraint. And that domain changes wake up the constraint. It gets invoked and performs its reasoning, its propagation, to see whether it's still satisfiable, and also to see whether domain elements can now be pruned, given the new information. That's exactly as intended, and that's of course also the point of constraints, to perform propagation or filtering to reduce the search space. That's good. And sometimes also quite costly. For instance, a filtering algorithm for a complex global constraint may be linear in the number of domain elements. Linear time sounds very efficient, right? But linear in the cardinality of the domain can be exponential in the size of the input, so it can be costly. At the same time, we of course want this filtering. So what can we do to make this more efficient? Well, let's look at these two goals. We see that first, circuit is posted on V's, and then another goal posts additional constraints on V's. And we know that propagation of circuit can be costly. So one easy way to avoid repeated propagations of circuit is to simply exchange these goals, like this. Declaratively, this means exactly the same, because conjunction is commutative. But procedurally, it's now more efficient, because now the expensive circuit constraint is invoked at the end, when all domains are already set up. And this is much faster, because it makes a difference whether propagation is performed only once or many times. And in Scryer Prolog, we can easily measure the difference with the predicate time, from library time. So this is our program. It describes a Knight's tour using the constraint circuit as the key idea. Let's now ask Prolog, are there any solutions for an 8x8 board? We get a conditional answer, yes, there are solutions if certain constraints can be satisfied. And it's deterministic. There's no alternative and not even a choice point. This is the only answer we get. And we therefore also know that the query terminates universally. Now, let's try to find concrete solutions by labeling the variables. Ready? Go. So, with this formulation, Prolog quickly finds a solution. We see here, for each square, the successor of that square represented as an integer. This makes it hard to see what the actual moves are, and therefore I will now show this a bit differently as symbolic outlines of knight moves, like this. There's an L-shaped knight move on each square, and that's the tour. And it's a closed tour, so we can also start from any square. And on backtracking, we get more and more solutions. So we see that we can now find many solutions very fast. Now, what have we seen so far? First, Circuit prunes the search space very effectively. We found many solutions with barely any search. Then, one nice feature of our formulation is that it automatically benefits from improvements to Circuit. So, if a Prolog vendor makes improvements to this constraint, then our program may become faster without any changes. And for instance, in Scryer Prolog, there's significant room for improvements, because currently it implements a very simplistic version of Circuit. When a domain changes, it only tests if there's still exactly one strongly connected component in the graph, because only then can there be a Hamiltonian circuit. So it only checks that a necessary condition is satisfied, whereas a stronger version of the constraint would go further and also remove domain elements that can't participate in any Hamiltonian circuit. It would filter inconsistent domain elements. It's a hard problem to recognize all such elements, prohibitively hard in general. But maybe there are efficient algorithms that would at least detect some of them. And such algorithms could be worth using if they strike a good balance between efficiency and strength of the propagation. And we also noticed that we had to pay a price. First, the other models we tried were wasted effort, or at least partly wasted, because we have reused a few ideas. But only the last model we tried actually found solutions. Luckily, Prolog makes it easy to try different models. It lets us write programs quickly. And also, we had to change our representation of tours to suit the circuit constraint, which doesn't strike us as very natural. It's probably not a representation we would have intuitively chosen. And finally, we also keep in mind that we are now only describing closed tours. That's a price we paid for using circuit. We may have excluded valid solutions. And it's somewhat ironic that ruling out a subset of solutions helps us to find solutions faster in this case, due to stronger pruning. And speaking of solutions, we now get solutions like this. A list of integers where each integer denotes the successor of the node at that index. That's not very readable, right? For instance, where's the first move going? It's hard to see. So let's relate such lists to more readable output. We want output that resembles a chessboard. And to start, let's relate such a successor list to what we could call an enumeration. Another list of integers where we can read off the order of squares more directly. A list where it's clear this is square 1, this is square 2, and so on. So that's a relation between a tour T's and the list E's, the enumeration. What must hold for E's? Well, first of all, T's and E's must have the same length. And second, we want to describe all elements of E's, and we can do this by folding over all elements of T's. And the state this time is a pair of integers. The first component denotes the index of the current element, in T's and E's. Initially, that's 1, because we start at index 1. And the second component denotes the number of the current element. So initially, that's also 1, because we simply call the first element square 1. It's a closed tour, so we can start anywhere. And the final state doesn't matter. What matters is only that if this holds, then E's is the enumeration induced by the tour T's. Now, let's describe the elements of E's. In fact, it turns out we don't even need the current element of T's. We only need the tour T's, the enumeration E's, the current state of our pair I0, E0, and the next state of the pair I and E. And this shall hold if the element at index I0 of E's is E0. So that's the key constraint to describe the enumeration. The integer at index I0 of e's is the current square number E0, okay? Second, I, the next index, is the integer at position I0 of t's. So here we refer to the tour t's, and that's why we pass it around as an argument. T's tells us the successor of each square. And therefore, since we are currently at the square with index I0, the element at index I0 of t's is the index I of the next square. And finally, the next number e in our enumeration is of course the current number E0 plus 1. And that's it. So let's try it. Let's ask Prolog for two t's and the corresponding enumeration e's. Here it is. So now we have the solution in a more readable form. Square 1, 2, 3, 4 and so on, okay? That's nice, but not yet in the form of a chessboard. And we can't simply print this list as 8 integers per line, because we would get this ragged layout due to the lack of alignment, because the integers have different numbers of digits. What we want is of course a layout like this, in the shape of a chessboard. And we can read off the tour, 1, 2, 3, 4 and so on, okay? How do we get this layout? Well, one way is to describe the layout with a format string, and that's what we'll do now. We are describing a format string depending on two arguments, an enumeration of squares and the number of remaining squares on the current line of text. So the first argument is an enumeration, a list. If it's empty, then we don't care about the remaining squares on the current line. We are describing an empty string in all such cases. And if there's at least one element e and possibly further elements e's, then we need to distinguish two alternatives. First, if there can be no more squares on the current line, and we represent this case with an empty list, then it's time for a new line. So here we use the control sequence tilde-n to denote a new line in a format string. We're describing a format string, not the concrete output. So we can use tilde-n here if we want to. And after this new line, there shall be a format string for all elements e and e's. And the second argument here denotes how many squares shall appear on the next line. So what should we specify here? Well, we could, of course, hardcode, for example, 8 squares for the next line, using any list with 8 elements, like this one, to symbolically encode 8 squares. But let's not hardcode this. Let's make it more generally useful for all board sizes by using an argument here, say row 0, that can be specified by the caller. Also here, an additional argument, which we ignore here. Okay? So on the next line of text, there shall be as many squares as there are elements in row 0. And we also pass along row 0 for future reference. So the second argument denotes how many squares can still appear on the current line. And in the third argument, we remember how many squares we want to write in every line, which is always the same, row 0. 0 as in the original line. And we pass this around so that we can refer to it when needed. And now the alternative. This is the case where there's an element e in the enumeration and also still enough room to write it on the current line. This is the case when there's at least one element in the first and in the second argument. And now we describe the format of an integer at this position. Let's say we want the integer right aligned. So we start with space to be filled to the left of the integer. Then tilde d to say an integer at this position. And at last we place a tab stop 3 characters to the right. For larger boards we could also extend this to say 4 characters. But for integers up to 2 digits, that's enough space. So this is the format we describe for one square. And this is followed by the remainder of the format string for the remaining elements e's and r's. And that's it. And so it turns out that we can describe the format string without caring about the elements of e's. Even here, for example, we could use an anonymous variable instead of e. We only care about the lengths of e's and r's. and we can reason symbolically about everything we need to know here. We don't even need arithmetic here. We only need to distinguish between empty lists and lists with at least one element. So this is our description of format strings. Now let's try it for a concrete example. Here we have 4 elements A, B, C, D, only the length of the list matters. And we are asking for the format string C's, a list of characters, such that there are 2 integers per line, hence 2 dots. And this is the format string, and there are no other solutions. It describes 2 lines. It contains 1 new line, and on each line there are 2 right-aligned integers. So that's not yet the output, but the format string we want to use to format the output. And this approach lets us observe the format string by itself in isolation. And this may seem a bit unusual because usually format strings simply occur hard-coded in Prolog programs. But here we describe the format string itself with Prolog code. And it shows that if we want to do it, then we can do it. We simply describe the format string like any other string, for instance, as we did here with the DCG. And to actually produce output, we can use, for example, the predicate format. The first argument is the format string, and the second argument is the list of arguments, in our case a list of integers such as this one. This succeeds with exactly one solution, and there's also output, the first line and the second line, formatted according to the format string C's. Now let's combine these building blocks to describe the output we want for 2 T's on an n times n chessboard, and we use a DCG again. First, we relate the 2 T's to the enumeration E's. Second, we say row must be a list of length n, and we use this to describe the format string fs. And finally, we state the string we are describing here, the output, is E's formatted according to fs, and that's it. And I invite you to think about this description. Are there more elegant ways to describe the output, or shorter ways? Was it a good idea to describe the format string separately, or should we maybe merge some of these building blocks? For now, let's ask Prolog. If V's is a knight's tour on an 8 times 8 chessboard, then what is the output C's? And in response, we get an answer, in this case a solution, that is ground terms for V's and C's, a list of integers and a list of characters, where C's is the output as a string in the readable form we've described. So we benefit here from the usual advantages we get from separating the description of the output from actually emitting the output on the terminal or to a file or network connection and so on. Because in this way we can easily reason about the output and test it, because it's available to us as a Prolog term. And if we really want to write the output, for instance to the terminal, then we can use phrase to stream to write the described characters to a stream, such as user output. And in our case we get this. Finally, a knight's tour in a readable form. We see the order of visited squares, 1, 2, 3, 4, 5, 6 and so on. This is a knight's tour, even a closed knight's tour. Now let's go back for a moment to the word model. As already mentioned, model has several different meanings. And it also occurs, for example, when we say someone has a mental model of something. For instance, what is our mental model of Prolog? Do we really know what Prolog is? It sounds easy, right? But it's not. It's easy to form a wrong mental model of Prolog. For instance, someone may see this thrashing and say, Prolog is terribly slow. Although the truth is that Prolog is as fast as we implement it. And speed is not a property of the language, but of an implementation. And it's true, Prolog is often applied to problems with very large search spaces. And traversing this space naively takes a long time, with every language. Another person, or even the same person, looks at this and sees many solutions found easily, and then says, Prolog, of course it's so fast, because it's such a highly specialized tool. Even though horn clauses are computationally universal, we can express every computation with Prolog. It's Turing complete. Another person, or again the same person, looks at this and says, Prolog is great for reasoning about strings. That's the only thing it's truly good at. And then maybe looks at this lambda expression and says, Prolog is mostly a functional language, and so on. So it's easy to form a wrong mental model of Prolog. How do we prevent this? One approach I sometimes see is to tell students, forget everything you know, about programming at least. And I understand it's tempting. When I see someone struggling with Prolog, then I'm sometimes also tempted to say this. Leave everything behind, forget everything you know. But that's not what I'm demanding. First of all, because it would be too hard. We can't really forget everything we know, right? And also because I want to encourage something more creative. I demand that we synthesize everything we learn, to combine everything we know and form a correct and complete mental model of Prolog. I know it's hard, and many of us are great at making terrible inferences. For instance, I've seen people who know that Datalog is a great database and query language, and that Prolog is a great programming language. And therefore, the semantics of Datalog and Prolog are completely different, right? Whereas a valid inference chain would be Datalog is a proper subset of Prolog, and therefore all properties of Datalog hold for that subset. And therefore, Prolog is also great for databases. This inference is quite easy, but still surprisingly hard. I know it's tough. Because on our journey, we'll see many things. Different Prolog systems with different features evolving over time. Many of them have great historic significance. There are also new systems with developing features and ideas. There are language constructs that are still hidden or at least partially obfuscated. Constructs that want us to find them. And as we learn more about the technology, we may have to adapt and even rebuild our mental model of Prolog again and again. And if anything, we should forget our prejudices and take everything into account and all connections so that we get to know what Prolog truly is. For instance, the constructs we see and new constructs we find may be more expressive than they appear. At first, we may have the impression that they are not very useful. But if we consider them more carefully, then we may find that we can apply them in more cases. For example, what is our mental model of the circuit constraint? Specifically, can it express also open tours? The answer is yes. And I leave this as a challenge. Use the circuit constraint to describe all Knight's tours. So that's an example of a language construct that is more powerful than it may appear at first sight. And in that regard, circuit is also a bit like a knight.